Hi again. So today we'll be looking at learning unit number 12, which is impulse and momentum. So here I've just got the plan for today. It's a short section. So we will start with impulse momentum theorem. But before we do that, it would be nice to define what is impulse and what is momentum. And then we'll use that theorem or derive it, and then we'll look at the principle of conservation of linear momentum, and then after that we'll just study collisions both in 1 and 2 dimensions, and then we'll go straight to so some questions from the study guide. Okay, so from the study guide, this is on pages 53, 54 and 55. So page 53, 54 and 55. Okay, so this is learning unit 12. Okay, so what are we studying? As I've said already, it's impulse and momentum. Okay, so what is momentum? So we will study what is called linear momentum. There's angular momentum as well, so which we don't study. So momentum. So by definition, linear momentum, actually we use P. So the symbol P, it's a vector, so we need the arrow on top. It's just the mass times the velocity. So that's the definition. We have already studied velocity, and we know velocity is a vector. Momentum is just velocity multiplied by mass, and it's measured in kilograms, so that's the mass unit, and then meters per second. Okay, so that's the unit for linear momentum. So what is this thing? So remember that if you've got a block and it's moving, say, in that direction with some speed v, the speed was something like 20 meters per second. So that's how fast the thing was moving. Now with momentum, so we just need to multiply the speed by m, where m is the mass of the object, and now this vector becomes momentum. Okay, so that's how momentum is, and of course you wouldn't say 20 meters per second, maybe the mass is 5, so we multiply the 5 by 20, so that the new the new vector is 100 kilograms times meters per second. Okay, so that's the definition of momentum, and you can see that even though I did not state it, momentum is in the same direction as velocity. Okay, so of course momentum is a vector, so in this case we need to add the fact that this is east according to this diagram. So your momentum would be 100 kilograms meters per second east. Okay, so and then before so by definition, impulse is given by the force acting on an object times the time at which, so how much time the force is in contact with an object. So these are mainly forces to stop an object from moving or to accelerate an object. So for example, if you have a tennis ball and it goes and it bounces, so it falls free fall, bounces off a surface, so say this is h1, and after bouncing, say it reaches a new height h2, which is then when the tennis ball was in contact, it experienced a force from the floor, and it would take some time t to lose contact with the floor. So then the momentum, or the impulse, sorry, is the F times t. Okay, so from Newton's second law, we have learned that F is equals to ma. So if F is equals to ma, what do we know? We know that acceleration is the rate of change in velocity. So now if I group so rate of change in velocity, if I now group the mass with the velocity, that's our definition of momentum, right? So I can just write F is equals to, because this is a change, I must also have a change, and then mv is just momentum. So then it's change in momentum over change in time, which is equal to the force. And you can see from here that the change in momentum will then be equal to the force times the change in time. Okay, so we called this thing impulse, and delta p is nothing but momentum. So this is known as the impulse momentum theorem. So this is the impulse momentum theorem. Okay, it tells us that change in momentum is equal to, or is due to the change, the applied force times the time at which the object is in contact with the surface in that case, or with the force. Okay, so that's the impulse momentum theorem. So if I can just show you the summary. So summary, we said linear momentum is p, and it's a vector, so it has an arrow. And we said p is equals to mass times velocity. So it's velocity multiplied by mass. We know velocity is a vector, and the unit is kilogram meters per second. And you can see that there's no negative sign in front of the equation. So momentum is in the same direction as velocity. And then from Newton's second law, we know that the applied force, or the net force, is the mass times acceleration. But acceleration is change in velocity over time. But we just said now that mv is momentum. So mv would be momentum, but we are studying a change. So then this would be change in momentum over change in time. If you multiply by the delta t, you get delta p is f times delta t. And this is the definition of impulse. And this side is the momentum. So we call this equation the impulse momentum theorem. And notice that there are two units of measurement that we have. So either Newton times second, or you use kilogram meter per second. Both of them are correct. So the Newton second comes from the force times the time, and the kilogram meter per second comes from the momentum side. Okay, so in our plan, we have just covered section 7.1. So now we are interested in the principle of conservation of linear momentum, and let's look at that. So we need a new page. So now we are studying the principle of conservation of linear momentum. Okay, so what does this principle tell us? It tells us that momentum, so for an isolated system, the total momentum is constant. Okay, so it's sometimes they use the word conserved. It's the same as constant. Okay, so that means if I have momentum at some time t1, later on at some time t2, so the momentum before was just p, after some time I must still have p, so the momentum doesn't change, okay, even though the time changed. So that's the conservation of momentum. But how do we write the equation? So we say momentum before, so I'll use a small b as a subscript, equals the momentum after. And this is a general rule, so it's always true. Okay, so how do we use this equation? If, say, for example, you've got two particles, the momentum before is the momentum of particle 1, which is the mass times velocity of particle 1, plus the momentum of particle 2, so the mass times the velocity of particle 2, and after it will be the momentum of particle 1, velocity of particle 1. Later on I'm going to use a prime just to differentiate this speed, this velocity from that, and then the momentum of particle 2 times the velocity, the mass of particle 2 times the velocity of particle 2. So that's how you would use the conservation of momentum, and that's this equation. Okay, so remember that vectors in general have an x and a y component, so that would be the x component and that would be the y component, so for the vector v. So let's call this vx and let's call that vy. So if v can be broken down into y and x, and we have conservation of momentum, so then we learn that we have momentum in both the x and the y being conserved. So we have p before in the x direction must equal the momentum after in the x direction, and then momentum before in the y direction must equal momentum after in the y direction. So what I've just written here is still conservation of momentum, but now it's in 2 dimensions. Okay, this here was in 1 dimension. Okay, so now that we have the conservation of momentum, now let's have an example. So an example would be something like, say you are playing pool with your friends. So remember that pool has 6 holes, so 1, 2, 3, 4, 5, 6. Okay, so there's a line where you can't, so where you place your white ball, say that's your white ball, and then over here you've got another ball, say it's the black ball, you're playing against your friend and you're trying to score the black ball. So initially the black ball is stationary, so it's not moving. What that means is the speed v naught of the black ball is equals to 0. The white ball, now you hit the white ball towards the black ball and you want, say you want to score the black ball in this hole. So you've bet with your friends that you are good enough and you can cut this ball so that it goes there. So before the speed of the white ball is v naught, and as a velocity I need an arrow, so say that's the case. And then if we are told that after hitting the ball, so remember actually let's draw a bigger table. Okay, so after playing, what you find, so there's our 6 holes, there's our line that we can cross. After playing, this was the original direction of motion for the white ball. The black ball does indeed, I drew it as blue, so let's be consistent. So if the black ball now does actually go in, but unfortunately for your friend, the white ball also goes in. So if this angle here is 45 degrees and this one is 45 degrees, with respect to the original direction of motion, the question then is, what is the total speed? So what is the speed v2? So let's call this white ball 2, the black ball 1. So that's 1, that's 2. And we want to know also what is v1. Okay, so let's assume, so you are told that the mass of the white ball is m and the mass of the black ball is m. So both have masses m. So then how do we study this collision? Remember that we have conservation of momentum in the x direction and in the y direction. Okay, but now which way is the x direction and which way is the y direction? That is up to us. And my advice to you is, when you study problems like this, always choose the direction of motion initially as your x-axis. Okay, so if our x-axis is over here, so that's x, then y has to be perpendicular, so that's y. So even here, that's x and that is y. So now momentum before in the x direction equals momentum after. Actually, it's smarter to start with the y in this case. You will see shortly why. So momentum before in the y direction equals momentum after in the y direction. Okay, so why did I say it's easier to start with the y? Because initially we don't have any y momenta, and afterwards we only have y momenta opposing each other. Okay, whereas initially here we have x momenta, and after we have y momenta. So there's 3 terms here, there's 2 terms there. So it's easier to work with this one. Momentum before is the mass of ball 1, which is m, that's the black ball, and the speed is 0, so it's just 0, and then plus for the white ball it's m, and then the speed or the velocity is v naught, so times v naught, okay, equals m, and then now the final speed is v1. So just to remind you, it's over here, so v1 for the ball plus m times v2 for the white ball. Okay, so this term is just 0, and then here we still have m. Now we need to substitute the vectors. So v naught is going in the positive x direction initially, so it's just plus v naught. Okay, the plus is the direction, the v naught is the magnitude. So that's the momentum before. This is equal to m, and remember that here we are looking at the x, so that's the x component, that's the x component, that's the x component. The x component of v1 is over here, so that's the x component of v1, and that's at an angle of 45 degrees. It's the cos of 45. So then I'll have plus, because it's going towards the positive x direction, it's plus v1. Wait, we're looking at y, so guys, that's y, that's y, that's y. So it's actually going up, so plus v1, and then it's going to be sine 45. Okay, so just make sure we are looking at the y conservation of momentum component. So then we for ball 1 it's going up, and we said up is positive for y, so that's why I have a plus there, and then plus this plus is this plus over here. Then I've got the mass of the white ball and multiplied by, now the y component is pointed down, which is opposite to the positive, so that's negative v2, and it's also sine 45. Okay, so now we can okay, so we were looking at the y, so this term over here um, should be 0 because we don't have a y component for the initial speed. The initial speed is only in the x direction, so that term shouldn't be there, it should be 0. Okay, so my mistake, apologies. So this term is just 0 because we are looking at y. So what we learn is 0 is equals to this term plus this term. Okay, so now I'm going to take the negative term to the other side so that it becomes positive. Then it becomes m v2 sine 45 equals m v1 sine 45. Okay, and then now you can see that the m's cancel, the sine 45 cancels. So we learn that v1 equals v2. So that's our first equation. Okay, and then to get the second equation, we use conservation of momentum in the x axis, in the x direction. So momentum before in the x equals momentum after in the x. Before it's the for ball number 1 it's stationary, so the momentum before is 0, it's not moving. And then for ball number 2 it's the m times v naught, and it's a positive because it's going towards the positive x-axis, so it's plus m v naught. After for ball number 1, which is the black ball, it's positive, so it's m, then the speed is positive v, remember it's v1, so v1 now it's cos 45 degrees. Okay, and then plus for the second ball the mass is m and the speed is also positive in the positive direction, so it's plus v2, and it's also cos 45. Okay, so if you check the cancel, remember that v1 is v2, so substitute v1 over there. What we learn is on the left hand side we just have v naught over here equals, and then here it's v1, and then this is also v1, so it's the same term twice, so I just get twice v1 times cos 45. So in the end our solution is v1 is equals to, so I have to divide by 2 and the cos 45. Cos 45 is square root 2 over 2. So this 2 cancels that 2, so I'm just left with square root 2. So v1 is equals to, I have to divide by square root 2, it's just 1 over square root 2 times v naught. Okay, so that's our final solution. So v1 is 1 over square root 2 times v naught, and most of the cases v naught is given, but we said v1 is v2, so which is equals to v2, so we have both v1 and v2, and that solves our problem. So how would you quote the final answer? So remember that v1 is a vector, so it will have the magnitude 1 over root 2 times whatever v naught is. Maybe v naught is 10 meters per second, then you substitute 10 meters per second here, and then the direction, if you check at your diagram, it's according to this diagram, it's 45 degrees north. So remember this is east, that's north, so north of east. Okay, so that is how we solve problems for 2 dimensions. Okay, so we are actually done with the material. We started off and we defined impulse, and we said impulse is force times, so it's applied force to change momentum multiplied by t. Then we said momentum is m times v, and we had a momentum impulse theorem, which is over here. So that was delta p is f delta t, and we said that's the units that we use, and it came from Newton's second law. And then after that we studied the principle of conservation of linear momentum, which tells us that if we have an isolated system, the momentum before equals the momentum after. You might be wondering, what is an isolated system and when is this true or false? So for example, if I have a ball floating in space, that's an isolated system. If I have two balls moving in space, that's also an isolated system. If I have a block on a surface, the isolated system, so the block is moving in some direction, is the whole system. So isolated system in this case would be the block plus the floor. Okay, so if there's friction on the floor, the block will lose some energy to the floor, and we have studied this. This is work done. The floor will then heat up, so that means the energy was transferred from the block to the floor. So as a system combined, the block and the floor would be an isolated system, whereas the block alone is not an isolated system. Okay, so the block alone is not an isolated system. So that's what I mean by isolated. And then we studied collisions in one dimension, and we studied collisions in two dimensions, and here we used an example of the pool table, someone playing the black ball, and then there's two more things that we need to discuss, which are part of the syllabus. So those two more things are the following. So there is something called an elastic collision, and we have an inelastic collision. Okay, elastic collision, all this means is the following. It means the following two things are true. So elastic collision, the kinetic energy is conserved. So kinetic energy before equals kinetic energy after. So, and this will depend on the number of particles, but in most cases you would have two. So if you have two particles, the kinetic energy before is 1/2 the mass of particle 1 multiplied by the initial speed of particle 1 squared plus 1/2 the mass of particle 2, the initial speed of particle 2 squared, and we said this is equal to the kinetic energy after, which is 1/2 the mass of particle 1 times the speed of particle 2, so that's the final particle 1 squared, that's the final, plus 1/2 mass of particle 2 times the speed of particle 2 squared. Okay, so that's the first thing that you have in an elastic collision. We have the fact that kinetic energy is conserved. Okay, and of course, so that's the condition for an elastic collision. Of course, we said conservation of momentum is always true, so we'll just add the fact that momentum before equals momentum after. So here we have m1, the initial speed of, the initial velocity of particle 1 plus mass 2 initial velocity of particle 2 equals that's the initial, so equals m2 final of number 2 plus the mass m1 times the final velocity of particle 1. So using these two in conjunction, you can then solve the two equations simultaneously to find the final speeds v1 and v2. Okay, so that's an elastic collision. And then what is an inelastic collision? Inelastic collision means the two particles move together after colliding. Okay, so assume we had a strange pool game or table. That would mean in our example that we did earlier, you have the white ball, there is the black ball. It hits, so the white ball hits the black ball, and then afterwards what you have is both the white and the black move together to whatever hole you have. So here of course you would win by not scoring, because if you score the black ball and the white ball you lose, so your aim here to would be not to score. Okay, so um, the other thing is that, remember that we said for elastic the kinetic energy was conserved. So here obviously the kinetic energy is not conserved. So Ek before is not equals to Ek after. Okay, so how do we do calculations here? So before, remember momentum is always conserved, so momentum before is momentum after. So before, say that's m1, that's m2, then here they are moving together, so you'll have mass 1 plus mass 2. So what you learn, actually this diagram is wrong. It should be moving in the x direction to conserve the y momentum, because before there was no y momentum, but it's just for the purpose of showing you how it moves. So here we will have the mass 1 times the initial velocity of particle 1 plus mass 2 times the initial velocity of particle 2. This is equal to, remember afterwards they stick together, so that means the total mass m1 plus m2 will then have a speed v. Okay, so that's the key. The key is afterwards these two would then move together. Okay, so now we have completed the section. Now we want to study some examples. Okay, so the examples I'm going to look at are from the study guide. So if you can now go to page 54. Okay, so page 54 of your study guide. In particular, we're going to start with question 1. So question 1 is, I'm looking at the tutorial questions. So can a single object have kinetic energy but no momentum? Explain your answer. Okay, so how do we answer a question like this? So we are looking at page 54, the tutorial problems. So these are tutorials, and now we are looking at number 1. Okay, so number 1 is asking, can a single object have kinetic energy but no momentum? So if I have one particle, can it have kinetic energy but no momentum? So momentum is 0. How did we define momentum? We said momentum equals mass times velocity. Kinetic energy was 1/2 mv squared. So v is the speed of the ball. So if the ball has speed v, that means it has velocity v, which means if I multiply the velocity, it has okay. So if I multiply the velocity by m, that means it has momentum. So the answer is no, it can't have kinetic energy and no momentum. Okay, so having kinetic energy implies that you have momentum. Okay, because both depend. So kinetic energy depends on speed, momentum is velocity. So having speed means you have velocity, which means you have momentum. So this is implied. Okay, so that's number 1. And then now let's look at number 2. So same page, number 2. Okay, so I should have swapped. So just to remind you, so we said if an object has kinetic energy, it means it has speed. What that means is if it has speed, it has 1/2 mv squared, but having speed implies you have velocity. Having velocity, if I just multiply by the mass, now I have momentum. So you can't have an object having kinetic energy and zero momentum. So having kinetic energy implies you have momentum, because kinetic energy depends on speed and momentum depends on velocity. So having speed, you have velocity, which means you have momentum. Okay, so that's number one. Then now number two. So let's read the number two. So number two says, can a system of two or more objects have a total kinetic energy that is non-zero, but a total momentum that is zero? And explain your answer. Okay, so here for number two, we no longer have one object, we have more than one. So if object 1 has kinetic energy EK 1 and object 2 has kinetic energy EK 2, the question is, can the total momentum, so that's the total kinetic energy, which is not zero, can the total momentum P1 plus P2 be zero? And of course, as you can guess already, I'm sure you're screaming your lungs off, the answer is yes. Okay, so how does this work? If we have the two balls moving either towards each other, or the two balls are moving away from each other, so as long as they move in opposite directions, and not just that, the added feature is the momentum. If the momentum of one is p, then the momentum of two has to be p as well. So here you can see that this is just p, it's a plus, so let's choose that direction as positive. It's plus p, then this one is moving in the opposite direction, so it's minus p. So then the total momentum is the sum of the two, so we get 0. And even here, if I have momentum p for 1, which is plus p, if I choose that as positive, then this one is minus p, so the sum is just p plus minus p, which is 0. But just a reminder, p is mv, so we do have non-zero v, so that means we have non-zero kinetic energy, so we'll have 1/2 mv1 squared plus 1/2 mv2 squared. Okay, so even though we have zero momentum, we have non-zero kinetic energy, because this term is positive, that term is positive, so the total answer is non-zero. So the answer for number 2 is a definite yes. Okay, so now number 3, we have a 0.5 kilogram ball which is dropped from rest at a point of 1.2 meters above the floor, and the ball rebounds straight upward to a height of 0.7. What are the magnitude and direction of the impulse of the net force applied to the ball during the collision with the floor? Okay, so now let's look at number 3. Okay, so number 3, we are told we have a ball. Let's assume it's a tennis ball. Initially it has a height of 1.2. It's dropped, so if it's dropped, that means the initial speed is equals to 0, and then it bounces off and it comes back to a smaller height, which is 0.7 meters. Okay, so now the question is, what is the impulse? Okay, so the impulse, we said, is the change in momentum, or it's also given by the applied force multiplied by the change in time. Okay, so the applied force would be the force of the floor on the ball. But how does this work? What is this T and where does it come from? When the ball is in contact with the surface, it deforms. So it deforms, and then it gains kinetic energy in the opposite direction. So initially it's coming in, and then it's deformed, and then it's pushed up, and that's how it works. Then it gains the shape back, and this part where it's deformed, it's in contact with the surface, and it takes a time t to lose contact with the surface, so it experiences a force F during that time. Okay, so that's the impulse, but in this case we don't have the force and we don't have the time, so we just need to calculate the change in momentum. So How do we then calculate the change in momentum? The momentum that it has as it hits the surface, that's our initial momentum. So we need the final speed as it hits the surface for this part. So here we need Vf, and that Vf is our initial for the total problem. So it's the final for this section, but it's the initial for the change in momentum. Okay, and then on the other side, we need the initial speed that the ball moves up with. So that's Vi, but Vi is the final speed for the total problem. So initially it hits the floor, that's why the Vf here is Vi, and then it leaves the floor, that's after, so that's the final speed, but it's the initial for this section. And also just a reminder that if the ball goes to a height of 0.7 meters, that means after 0.7 meters, which is Vf, the speed is 0, so it stops. Okay, so we need to choose a direction of motion. Let's choose down as positive. If we choose down as positive, g is equal to positive 9.8 meters per square seconds. Okay, so now let's use equations of motion for this half to find Vf. So we know Vi, we know h, and we want to find Vf, we know g. Okay, so there's no t, then the equation of motion that we use is Vf squared equals Vi squared. So I'm looking for section 1, so problem number 1, plus 2gh. Okay, so and then we said Vi is 0, so that's 0, and we are looking for Vf, so Vf is just 2gh, and if we just plug in the values, it's 2, g is 9.8, it's positive because it's going down, so it's positive, and then h is also positive because the displacement is in the direction of motion, and it's just 1.2. Okay, so let's plug that in. So we've got 2 times 9.8 times now we need 1.2. Okay, so we get the answer, and then just remember that that is v squared, so we need the square root of the answer, and that would be our final answer. So when you've got an answer like this in your calculator, just press the SD button, so it changes a fraction into a decimal, so that's the decimal, and we find 4.85. Okay, so because Vf is down, it takes the positive, so Vf will then be plus 4.8. Okay, let's just switch. So I just want to remind you, because Vf for this portion is down, it takes the positive, and Vf here would then be plus 4.8, and the next value is 5 meters per second. But just a reminder that Vf is actually the initial speed for the change in momentum. Okay, then now we are going to look at 2. So for 2, we know the final speed is 0, we know the height is 0.7, we know g, we want the initial speed. So again we use Vf squared equals Vi squared plus 2gh. Okay, so in this case Vf is 0, so we have 0 equals, and then the initial speed is what we want, so Vi squared plus 2, so g is positive because it's going down. We said down is positive, so that's positive 9.8, but h is up, so it's negative. The displacement is in the opposite direction of our positive, so negative 0.7. Okay, so you might be worried how we're going to have a square root which is negative. Actually we won't, because if you take this to the other side, the negative becomes a positive. So now Vi, if you just plug it in, so just press 1 and then you have 2 times 9.8 times 0.7 and you get that's VI squared. You need the square root of the answer and remember to press the button. Then it's gonna be 3.70. So we get VI is equals to, and remember that VI is going up, which is negative, so remember that. So VI is equals to negative 3.7. Okay, so negative 3.7 meters per second. Okay, and again a reminder that the initial speed for the second part is the final for the whole problem. Okay, so what is the change in momentum? Change in momentum, which is the impulse now, will be the momentum, so the final momentum minus the initial momentum. Okay, so what is this equal to? The mass of the object is given, it's 0.5, so the mass of the ball is 0.5 kilograms, so multiplied by the final speed, and the final speed, just a reminder, is this one. So we have negative 3.7, so the sign is important because it's a vector, and then we have the minus from the equation, and the mass is still 0.5, and now the speed is the initial, which was a plus, so plus 4.85. okay, so then what is our final answer? So now let's plug it in. So we have 0.5 multiplied by negative 3.7. So if you have negative, you use this negative and not this one. So times negative 3.7, close the bracket, and then this minus is for minusing the sign in between. So and then times 0.5, 0.5 times 4.87. Okay, so 85, and this was the positive, so I won't put a plus there, I'll just leave it as that, and the final answer is negative. So we get the impulse is negative, so we get the impulse equals negative 4.275 Newton second. So what does this mean? Remember that positive was down, so it means because we have a negative, it's up, so the final answer would be 4.275 Newton second upwards. Okay, so that's the change in momentum. Okay, I just want to point out that the answer in your book is incorrect, so just correct that. The correct answer is 4.275 Newton second, and it's upwards. Okay, so now let's move on. We are almost done to question 4. Let's actually skip question 4 and go straight to question 5. Okay, so question 5, also there's a mistake in the solution, especially the second equation. One of these two should be a minus, but we will see how that comes about. So number 5, we have a hockey puck B, which rests on a smooth ice surface and is this should be struck by a second puck. Okay, A, which is originally traveling at 30 meters per second and deflected 30 degrees from its original direction. Then puck B acquires a velocity at 45 degrees relative to the original velocity of A. The two pucks have equal mass, and we need to write down the equations to determine the unknown velocities after division. Okay, so let's see what we have. Okay, a new page. So this is page 55, number 5. Okay, so page 55, number 5. What we have is so we have a park which I'll draw as a box, park B, and it just rests initially. Then another one, A, is actually moving at 30 meters per second, so 30 meters per second, and it hits this one and then they are deflected. But you can see from here that I'm drawing the side view, which is quite difficult to see, to bring in the angles. So I'm going to draw the top view. So imagine that that is how it looks like. There's our A and there's our B. So A is coming in at 30 meters per second, and remember that these two have equal masses. So this has mass M, that's mass M, that's mass M, and this one initially just rests. Okay, so what I'm gonna do is I'm gonna choose X, as I said earlier, as the direction of motion, and I'm gonna choose Y as the perpendicular to that. Okay, so what happens afterwards? Afterwards we are told that this was the initial direction of motion for A, that one of them goes at an angle, so let's say that is A. A goes at an angle of 30 degrees. Let me just double check to make sure. Okay, so A is deflected at 30 degrees to the original direction, and B is deflected at 45 degrees. So it's similar to our pool example. Okay, so now let's call this speed VA or velocity VA, and this velocity VB. Okay, so how do we solve this problem? We are going to use conservation of momentum in 2 dimensions. So let's start. So momentum before equals momentum after. Okay, so, and this is in the we start with the y direction because it's easier. Okay, and in the y direction you can see, so that is x and that's our y. You can see that initially there's no components over here, so 0 for A and it's 0 for B. Then afterwards for A, y is up, which is positive, so it's m, and then for the speed it's positive. The magnitude is VA. I want the y component, the angle is 30, so it's going to be VA sine 30 degrees. And then I've got plus from the equation. The mass is also m, but now the other one is going down, which is negative. The magnitude is VB, so negative VB, and the angle is 45, so sine 45. Okay, so taking this to the other side, I learned that m VA sine 30 equals m VB sine 45. Okay, so that's one of the equations. But if you like, you can leave the equation in this form, and you can see why I was saying the answer in the book is wrong, because we have a minus for one of them. Okay, and notice that this is not unique. You could have drawn your diagram so that, remember, that was the direction of motion, so that A actually is below, so the 30 is over there and the 45 is over there. So that's equally correct. Okay, so that's our first equation. And then our second equation, we just use conservation of momentum in the x direction. So momentum before in the x direction equals momentum after in the x direction. So before, the momentum in the x direction is just for A. So we've got, let's call this speed V naught. So it's mass of A, which is m, times the speed, which is V naught, and the speed is in the positive direction of x, so this is a plus, and plus this is resting initially, B is resting, so plus 0 equals, then the momentum after for the x components for both, so you can see that the x component for A is that direction, the x component for B is that direction, which both are positive. Okay, so it's mass of B. Actually, let's start with A. Mass of A times the magnitude of the speed for I mean the magnitude of the velocity for A, multiplied by, now it's going to be cos, so for A the angle is 30, cos 30, okay, and then plus the mass of B, it's also positive, so I should put a positive there, and then VB cos, the angle is 45, so 45 degrees. Okay, so our second equation, you can also see that the mass M cancels out, and remember that V naught is 30, so we learn that 30 equals VA. Cos 30 is square root 3 over 2. Cos 45 is square root 2 over 2, but I won't put them in, so VA cos 30 degrees plus VB cos 45 degrees. Okay, so that's our second equation, which is over here. Okay, so that completes the problem, which is question 5. Okay, question 5 and question 7 are the same problem, so I would advise you to do problem number 7 on your own, and the hint that I would give is call this direction your x direction. So the direction of motion initially for the rocket is x, and the other hint I would give is because just remember that they said the rocket suddenly breaks up into two pieces of equal mass, so call this one m, call that one m, so it breaks up into two equal masses, which is m and m. So going backwards, you can see that the total mass was m plus m, which is 2m. So you have 2m here, you have m there and m there. And then again, it's conservation of momentum in the x direction and conservation of momentum in the y directions, and then you will be able to solve v1 and v2. So just like here, if you check this equation, I can write, okay, here I should have cancelled the m's. I can write VA in terms of VB, and then by doing what? By dividing by sine 30. So then we would learn that VA equals VB sine 45 over sine 30. And then I would use this answer in the second equation. So where there's VA, I just substitute this number and I can solve for VB. After solving for VB, I then substitute back VB over here to find VA. And that's how you would find V1 and V2 for problem number 7. Okay, so now let's look at question number 6. So question number 6, we are told we have a half kg bullet of mass. So the half kg is the mass. It's fired horizontally, so there's the bullet. It's fired horizontally at a speed v naught, and which is 45 meters per second at a stationary wooden block. So the block is initially stationary, and it has a mass of 10 kilograms. As soon as the bullet hits the block, it instantaneously stops. So that means they move together. As soon as the bullet hits the block, they start moving together. Okay, so you can imagine. Oops. Okay, my mic just fell, so sorry about that. So you can imagine that what you have is something like this. There is the block, there is the bullet. The bullet comes, it hits the block. As soon as it hits the block, they are both stationary and they move together. Okay, so let me demonstrate that on the screen. So what I mean is that, so what you imagine is there's your block, there's your bullet coming in, and as soon as the bullet hits the block, so that's the bullet block system, they then move together with the same speed v. Okay, so you can see that the total mass of the two is the mass of the bullet plus the mass of the bullet, the block afterwards, okay, times the speed. So this looks similar to inelastic collision. In fact, I think it is. So let's see what the question is. So the question was okay, so the block with the embedded bullet slides along a horizontal surface with a coefficient of 0.125. Part A, we should determine the speed, the takeoff speed of the block with the embedded bullet. So for that we'll use conservation of momentum. We know the momentum before, it's just this plus 0, and then after it's the momentum of the bullet block system, so we can find V. Then how far does the block go or slide before it comes to rest? For that part we just use work and energy, because we know that all of the energy of the bullet block system is lost to the surface. Okay, so let's start with part A. So once again, page 55, number 6. So part A, the momentum before equals the momentum after. This is in one dimension, so there's no need for x and y. And then before, it's just the mass of the bullet, which I'll call small m. For the block, I'll use big M, times the speed of the bullet, which is v0. So call that direction. The direction of motion is positive. So here this is a plus, and then plus the block is just resting initially, so plus 0 equals, after they move together, so the total mass is m plus m and the speed is v. So we are looking for the velocity v, but now just a reminder that afterwards they move in the same direction as the block, which is that way, so this is just plus, so I don't need the arrow. Okay, so what we find is v is just, I need to divide by this m plus m, so I find m v0 all over m plus big M. Okay, so if we substitute, remember m is a half, v0 is 45, and then m plus m, big M is 10, so half plus 10. Okay, so what does this give us? This will give us, let's see, so we have a half times 45 over 10.5, which is 10 plus a half, so what we get is 2.14. Okay, so our final answer is V is 2.14 meters per second. Okay, so what that means is the final speed of the, or the initial speed of the bullet and the block is equals to 2.14 meters per second in the direction that the bullet was moving. So here I'll just use east, so it's east. So the bullet was initially moving east and the bullet block system also moved east. Okay, so that's conservation of momentum. And then now for part B, how far do they move? For that, we know that the frictional force times the distance, which is the distance of how far they move, times cos theta is equal to the change in kinetic energy. So here I'm using the work energy theorem. So work is force times distance times cos theta, and it's also equals to delta Ek. Okay, so from this side, frictional force is just mu k n, but for the block in the y direction, it's only the weight and the normal force that are acting. So n is just mg. So I'll just rub off the m and substitute mg. So mu k n, and then now we've got s, and the angle between, so remember that the frictional force, there's the block, frictional force is acting in that direction, the block is moving in that direction, so the angle between friction and displacement is this one here, which is 180 degrees. Cos of 180 degrees is just minus 1, so then I've got multiplied by minus 1. This is equal to kinetic energy. Remember that change is final minus initial. Finally they stop, so it's 0, then initially it's minus 1/2, and okay, so here remember that the mass that I put here should be for the bullet and the block, so it's m plus big M. Okay, so even here it's m plus m. That's the kinetic energy of the system, and then multiplied by v squared, and this v squared is the initial speed we've just calculated over here. So the m plus m cancels on both sides. The minus 1 cancels that minus. So then what we are left with is that s equals, this side I've got vi squared over, there's a 2, so 2, then I need to divide by mu k and g, so 2 mu k g. Okay, and then substituting, remember that we said it's 2.14 for vi, so 2.14 squared over, I've got a 2, mu k is 0.125 and g is 9.8. Okay, so plugging these in, what do we find? We find the following. So we've got 2.14, so 2.14 squared times, there's nothing else, so at the bottom we have 2 times 0.125 multiplied by 9.8. Okay, so if you multiply those out, you get 1.869 meters. Okay, so S is just 1.869 meters. Okay, so that's the two solutions. The speed was 2.14 and S is 1.869 meters. Okay, so that completes today's lesson. What I would then advise is that you check Blackboard. I will put a solution for number 3, which is a tedious question from page 54. So page 54, from the problems that you do with the lecturers, number 3 is a long question and it's elastic collision. So we use a combination of conservation of kinetic energy and conservation of momentum. My solution, which you can see over here, is a very long solution. Okay, so kinetic energy is conserved and momentum is conserved. So what you have initially is ball A is moving at 0.4 meters per second towards ball B, which is just resting, and they want to know how do they move afterwards, and that's my solution. But how do we get that? We start off and we look at momentum before and momentum after, and it's just one dimension. So before, only A is moving, and it's moving in what I've called the positive direction, which is the direction of A. So I've got the mass of A multiplied by the speed of A, which is positive, plus 0 because B is resting, and then equals the mass of A times the speed of A plus mass of B times the speed of B. That's after the collision. Okay, so if I substitute now, there's the mass, there's the mass. I don't know the velocities, so I leave them as vectors. Then here you can see there's a common 0, 1.5 and even there, so I just divide by 0.015 because it's a small number and it can be irritating working with them. So here I'll be left with 0.4, then I only have a VA plus 3 because that's 45, this is 15, so dividing this by 0.015 you get 3, and from this you can see that I can write VA in terms of VB, so it's just 0.4 minus 3 VB. Then now we use conservation of kinetic energy. Kinetic energy before is kinetic energy after. Before is just A that is moving with a speed of 0.4, so it's just 1/2 ma v squared, and the 1/2s you can see also cancel. So and then B is just stationary, so plus 0, and afterwards it's just the kinetic energy of A and the kinetic energy of B. So I've just cancelled the halves, and then for A I've got the mass is 0.015. There is the initial speed, don't forget to square. For A after, I've got the mass. Then just remember that VA we've just found from conservation of momentum in terms of VB, so we want to solve them simultaneously, so substitute VA for VB so that you only have one unknown. Okay, so substituting 0.4 minus 3 VB, this is a scalar, we are talking about speed, so you lose the arrows. Okay, so you square that plus 0.045 and then times VB squared, and then just manipulating these two, you will find that the final answer for VB is 0 or 0.2. So 0 is when this is stationary, 0.2 is the final answer, which is positive, and then substituting the 0.2 in this equation, we get negative 0.2, which means A is moving in the opposite direction it came in. So that's how you solve the problem. But I will just scan this solution and email it to you. Okay, thank you for having me.